So today we're working on functions. Now, the reason why we're working on functions is it makes a lot of things very easy for us later on. What you need to realize is a function is a relation, which really is a pattern or relationship that exists between two variables. These relations, when you think about them, they can be expressed with equations, tables, or graphs. We're literally going to do as many of these as we can. Now, a function is a relationship between two variables where each value of the independent variable has exactly one variable, x, and exactly one variable, y. Essentially, we have one x for every y. Graphically, it basically tells us that any vertical line drawn through the graph should only touch one point in the graph of that relationship. Now, how does this relate to our original things that we were looking at? Remember that our original equations that we were looking at were something like this. Y is equal to ax squared plus bx plus c, and we called these, remember we used to call these quadratic equations, and now we're going to create quadratic functions. Now, the fact that I'm talking about equations, tables, and graphs, this is our equation. We can have a table like this of points, or a graph that we'll fill in a bit. So now let's try to figure out what a function means in terms of tables and graphs. You'll notice that this graph in our x column has unique x's. X is 2, 4, 6, 8, 10, and 12. There are no repeating x's. The moment I see something like this in a table, organizing all our x's from smallest to largest, this tells me that this is what we call a function. These points that are represented, which I could plot on a graph, is a function. This graph here has a slope of 1, -1, 2, and its y-intercept is 1. Therefore, the equation is y equals -1/2 x plus 1. Now, let's talk about this graph. Remember what I told you? I told you earlier that this thing means a function is basically, if I have a vertical line drawn through the graph, it should only touch one point along the graph of the relationship. Now, if you think of this graph here, y equals -1/2 x plus 1, the two arrows at the end of the lines means that it goes on forever. Now, I've created my handy-dandy vertical line. Otherwise, you would call it a ruler. So what I'm going to do is I would take a look at my graph and I would move my ruler across this graph, and I would always check, yes, we have exactly one point touching the vertical line as I move it across the graph. If I can guarantee this, that means this is a function. This is a function because y equals -2x plus 1 passes the vertical line test. So we automatically assume it's a function, because as I move this point across the graph, this ruler across the graph, it touches the graph at exactly one point all the way across. So just to clarify, VLT is the vertical line test as I've indicated below. Now, it goes to show that most cases for lines, straight lines are always functions. I just want you to remember that. Straight lines are always functions, save for one special case, and we'll experience that later on in the semester. But for right now, that's it. Now let's move on to the next examples that we have on this chart. Now, again, we'll take a look at a table of values, and what we'll do is we'll go through the table of values, and remember, a function for a table must have unique x values. There must be exactly one x value for everything in this column. But you notice right away we have two of the same x's. Notice we have a matching x here with a corresponding y value, and we also have another x here with a corresponding y value. When you indicate these for me on assignments, the best way to do this is to indicate this, and you're going to say not a function. This is not a function since two y's have the same x value. Another way to represent that would be to do our vertical line test. Now when we take our ruler and we move it across this new graph, which is just a circle, you'll notice as I move across the graph, there are 2 points. You can find 2 points along the graph where, as you move this across, it will have, for every one x value, you're going to have 2 y values. Much similar to what we found here. We found one x value with 2 different y values. So this circle, based on our vertical line test, shows us that this is not a function. So now you just say the circle isn't a function, and since it failed the vertical line test. And anytime you see a circle, you'll always have a vertical line test that fails. For example points, I could say that 0, 8 and 0, -9 are proof because, just like before, I have one x, i.e. 0 is our matching x, but we have 2 different y values. And that basically will tell us, based on our vertical line test, that this fails. Our circle in this problem is not a function. So now what we're going to do is we're going to talk about the domain of a function. The domain of a function is just the x coordinates, the possible x coordinates of the function. The range of a function is just the possible y coordinates of a function. Now, a function could, remember, be a table, an equation, or a graph. So we're going to take a look at some examples. Now, if I consider this equation here, this equation, p is equal to 8h. Now, the reasonable domain and range is basically calculated by figuring out what values are for the independent variable h. H is what we would call our x. So we would say the domain for our equation is this. We write the following: h, which is the variable we choose on the right side of our equation here, and this straight bar up and down we call such that. Well, think about it. Can I choose a really, really big number for h, like say 1 million? Could I take 8 and multiply by 1 million, and would it work? Yes, perfect. Let's take a look at 0. Does it work for 0? It works for 0 as well. If I punch in 0 here, 8 times 0 gives 0. That works too. Let's say I took negative 1 billion and multiplied it times h and substitute it into this equation. We get negative 8 billion. So in that case, this means h can be any real number. So we just said here that h is h such that h is any real number. So now the mathematical way of writing that would be h the bar, which means such that h epsilon with a double script r. That is telling us h can be any real number. Now, if I looked at all the choices that I had for h now, remember we chose h to be negative, right? So when I multiplied this, p was either ridiculously positive, 0, or ridiculously negative. So the same could be said for our range, which is all the values of p. So our range is equal to, well, p such that p is an element of all real numbers, exactly like what we said before. Now let's take a look at some problems that we have in table form and graphical form. So when we have a table, we take a look at our graph and we always check. First of all, is this a function? Well, we got a 3, a 5, a 7, 9, 11, and a 13. Hey, it is a function. That's great. So we have unique values of x. So guess what? This doesn't matter what these numbers are. As long as these numbers are unique, these x's are unique, we have a function. So this table here is a function. That was just a throwback to what we did before. Now let's take a look at the rest of this. The next thing we have to do is we have to look at the domain of a table as a list of all the x values that are in the table. And this is how you would write it. For this problem, you would say the domain is just going to be a list of numbers. And it's just the list of numbers of x. So you'd go, you wouldn't have to write x such that blah, blah, blah. Just write in all the numbers. Just write 3, 5, 7, 9, 11, and 13. Because it's a series of points, the domain is just all the x values in our table. And so for our range, we can say the same thing. But remember, the range is dealing with just the y values and all the y values that are available to us. So now I'm just going to list all my y values and I'll read them and write them in order. 3, 7, 11, 15, 19, and 23. And there we have our domain for our table of values. All right. Basically, what you should do when you take a look at a graph like this sometimes is you take a look at it and you see that it is a straight line. Now, remember, I told you, anytime we have a straight line, say for a special case which you don't know yet, just remember, if you have a slanted line or a horizontal line, your domain is always going to be x such that x belongs to all real numbers. Because if you took a walk way out to the right here, and I extended this line on forever, I could eventually walk all the way up, walk all the way across, and then walk all the way up and touch that line. And I could do the same going ridiculously negative and all the way down, and eventually I could find a point that touches the line that has the same x that I just found here. So our domain is going to be x belongs to all real numbers. Now we'll do the same for our range. Our range for any straight line unless we have a special case, is always going to be the set of values that y can take. And you'll notice that y continues to increase forever. And then it also goes down forever as well. So it increases forever, but it also decreases forever. So that means it's going to take up the entire real line. So we write y such that y belongs to all real numbers again. So remember, anytime we're dealing with straight lines, that is what we have. Alright, now let's take a look at these next problems here. Now we have a horizontal line. I love horizontal lines. Horizontal lines are the best function ever. Now, if you have a horizontal line and I walk all the way across on the x-axis, its domain goes on forever. For any x I choose here, I'll always find a point that's going to be on this line. So I do the same thing for this. And now our domain for this straight line is still going to be x such that x belongs to real numbers again. Now, as for the range, range is telling us what our y values are and our x values are. Now, if you take a look at this equation, something particular has happened here. Something very peculiar has happened. There are no other y values. Every number that goes along this line, y is always 3. So guess what we say? Y such that y equals 3. And we're done. Now let's take a look at this parabola. Parabolas are great too. When we take a look at a parabola, you'll notice that my parabola, I've set it up to be swooping down and going up. So imagine, let's see, I walk across the line, and every line I point, every place I go, all the way to the right, say 1,000,000, I can easily find a point way off the page that will eventually touch this line, touch this parabola that goes on forever. The same can be said going the other way. So here's a rule. Anytime you have a parabola, for a parabola, basically what you need to know, the domain is always this. X such that x belongs to all real numbers. Now, let's take a look at the range of this parabola. We either need to find the highest point on our parabola or the lowest point on the parabola. So you'll notice this parabola swoops down and then goes back up. So there's got to be a minimum here. If you look at it, there's a minimum. What's the minimum value in this case? Right. You guessed it. The minimum value is y. But you notice it goes up forever. So it always gets bigger and bigger numbers. So in this case, anytime you have a parabola that's opening up, the parabola is always, for its range, is always defined by either its lowest point or highest point. And in this case, our lowest point is y is 0. So in this case, we're going to say our range, where our y values take, are as this. Y such that y is greater than or equal to 0. And y is any number on the real line. So basically, all the numbers that are bigger than 0. That is what we always say for parabolas that open up, especially when we know where their bottommost value for y is. In this case, it is 0. Now, I've had some students ask me a long time ago, let's take a look at a set that is not a function. So when you hear the term of an ordered set, we're talking about points from a chart. So imagine, let me show you an example of an ordered set that is a function. So for example, let's say I had this set. So you have a list of points, which is what our squigglies mean. I got a list of points, and these are the points. So here are the points. Ready? The list of ordered points. They are ordered. X is first, and then Y. So let's go 1, 0. There's my first point. Next point, 2, 5. The next one could be 3, 10. The next ordered point could be 5, 20. And it could go on forever as long as all of the X's are unique. There's exactly 1 point for each X. 1 point for each X. Now, let me give you an example of a set that isn't a function. An example of a set that isn't a function is this. So imagine I have a set of points that look like this. 1, 0, 2, 5, 2, 6, 3, 6, 5, 6. You'll notice that when you get these sets, it's always great to organize them from left to right where our X's are the lowest value. Okay? Now, these are the two offending points. Notice I have 2, 5 and 2, 6. These are my offending points. So if I chose X is 2, this means this is not a function, because if I had X is 2, it could either be 5, my Y value could be 5, or my Y value could be 6. So if I had plotted these points on a graph, you'd see that this is not a function, because X has two possibilities for Y, 5 and 6, and so this is not a function. What I'd love for you to do is take a look at question number 19, 1 to 3, 11, and 20, number 6. Good luck, guys.